This course is a detailed introduction to system design for software developers and engineers. Gaurav Sen developed this course. He is an experienced software engineer, and he also has a popular YouTube channel. You'll learn about basic engineering design patterns that are used to build large-scale distributed systems. In the second part of the course, you will learn how to use the principles from the first part to design and code a live streaming video app.
Hello everyone, welcome to this system design course. This course is for beginners in a sense that if you have never done system design before, or you have done very little system design, or you have just heard of it or read about it but not got an opportunity to actually do it, this course is right for you. At the end of this course, you'll be able to identify some basic engineering design patterns which are used to design large-scale distributed systems. Let me define each of these terms in detail. Large-scale distributed systems. As the first part of the term says, large scale, meaning that something which is being used a lot or is very intensive in terms of compute or data or any computer engineering principle. For example, Google, let's say Google Maps. This is large scale because A, it has a lot of data. The whole world's map has to be stored inside it. B, it's being used by a lot of people. C, it's being updated very frequently. And D, it has a lot of performance expectations from it. You don't expect Google Maps to go down. You expect Google Maps to return results quickly. You expect it to be accurate, so on and so forth. So it's a very good product being used at a large scale. Distributed systems means that the server or the code that is actually executing this program is not in one place. It's distributed all around the world. So you might have one server in India, one server in the US, one in Japan for fault tolerance, so that if one of these servers crashes, the rest of the servers can take the load. It's also for performance. If the Indians want a Google Map result, they go and talk to the Indian server because that gives a quick result back. While if they go to the US server, they have to go across continents and then get a response, which is a slow result. Okay, so that's the point of a large-scale distributed system. Many of these companies which provide these solutions expect their engineers to know about system design, to know how to build these large-scale distributed systems. So to do this, their engineering team depends on design patterns, which we mentioned earlier. Design patterns are particular practices, principles, or processes which are used by engineers to build these systems. For example, you have a common problem of a celebrity posting on social media and that post being distributed to a lot of their followers. For example, if Brad Pitt posts something on YouTube and then posts it on LinkedIn, the problem is very similar. It's one piece of content which has to be made into an event and notified to millions of people potentially. And what you want to do is you want to notify them quickly, but you also don't want to put too much load on your service so that the rest of the requests which are coming into it continue being served. This is a common problem. So you extract out a common problem and you solve it using a common solution. This would be a design pattern. Right now, you don't know what design patterns exist, but one popular design pattern for this kind of a problem is a publisher-subscriber model, where Brad Pitt is a publisher and their event is subscribed to by millions of people. An intermediary decides the pace at which you send these notifications, which keeps the server load low and also makes sure that all the notifications actually reach all the subscribers. Now, seeing this, you can tell that as an engineer, you can take a lot of business requirements and convert them into technical solutions. And engineers use system design patterns to make reliable, scalable, and maintainable systems. This helps them convert business requirements into technical solutions. If this sounds exciting to you, watch the rest of the video and you won't be disappointed. Okay, let's start with an example. Let's say that you join a company which does broadcasting of videos to millions of people. This could be Hotstar, it could be YouTube, it could be Zoom also. So some sort of events which are being broadcast to millions of people. And you as an engineer have to devise the solution for this, come up with some technology which can handle this problem. So the first thing that we need to do as engineers is to define these requirements from the user's perspective. And often engineers don't do this. There are product managers in a company which write a product requirement document based on user feedback and data. So that's good to have. You have a well-documented, well-thought, business-backed document, which the engineer can then read and decide on how they can make it happen. Amongst these, you pick up the most important features first. Taking the example of a live streaming system, users who tune into your system should be able to watch the stream live. Whether you see it at HD quality or you see it at 480p, that's probably a secondary issue, but being able to see the video is a primary issue. So for that, you have to make sure that your server doesn't go down, and you have to also make sure that your bandwidth requirements are sufficient. Second, you reduce these features to data definitions. So one of the features which might be defined is users should be able to like a video or should be able to like a comment. What you then do is you look at the concept of a like, the abstract concept of somebody liking something. What does that mean? It means that a particular user likes a particular comment. Okay, so it has a like ID, it has a user ID who's done this, it has a timestamp, when was this video liked or when was this comment liked. The comment itself is an abstract concept. It's probably going to be mapped into an object. It has an ID, it has a user who has typed this comment, it has a creation time, and maybe it also has a thread in which it was posted. So you're seeing that I'm taking features, or I'm taking these abstract concepts from the product requirement document and converting them into data definitions, which are useful for an engineer. These definitions can then be mapped into objects, which can then be mapped into the database. Once you've defined the data that you need to store, you need to define endpoints through which this data can be manipulated or queried. So I want to read comments. Give me an API, an HTTP API, FTP API for all we care. The network protocol at this point is not important, but some method by which I can send an electronic signal from one place to our server, and our server can respond to that signal with the data that they need. So our server is now encapsulating this data as per the user requirement and defining some endpoints, which are called APIs, so that external users can query and manipulate our data. We do this for every feature that we have, core features and also optional or good to have features. Usually a product requirement document does not define optional or good to have features. These are all core features which are required in the document. The good to have features will be probably picked up in the next document. So you don't need to think of which features are optional, but you do think of which features are most important as an engineer. The second thing is you also have certain engineering requirements when you're creating these designs or coming up with some code. You want to make sure that none of your services fail if there is an outage. So for example, if you have an outage in India and your comment service is in India, then you don't want the entire system to collapse. We talked about this a little earlier, that you have multiple servers spread across the world to avoid a single point of failure. You may also have multiple servers in India itself. So if one Indian server fails, another one picks up its responsibility. So here you might have some sort of data duplication, because of which the other server is quickly able to pick up the responsibility. Or you have some sort of partitioning that 50% of the users are going to this server, 50% of the users are going to another server. So just 50% of the users are affected. Another common and often missed out engineering requirement is extensibility, which means it's not just about the technical solution that you come up with, but also how easy it is to change that solution. For example, if you write code to send a message to millions of users, and you need to make a small tweak to that code, because now you don't want to just send it to 1 million users, you also want to check whether they have read those messages. So a read receipt. The problem with writing code which is highly coupled with the feature is that whenever there's a changing requirement, you have to put in a lot of effort to redesign, test, and actually deploy that code again. So you want your features, your engineering features, to be extensible. For this, you have to take out your engineering crystal ball and gaze deeply into it. Actually, what you do is, as an experienced engineer especially, you look back at your past projects, you look back at things that you have done, you look back at things that people have done, what the world is doing. And based on that combined knowledge, you build a system so that you can reasonably expect it to scale and extend as requirements change and as more and more users join you. Finally, this design needs to be tested. This is an important part of system design, which is not really thought through in interviews. But in the real world, when you have a system, which is designed by, let's say, a senior engineer, that design has to be tested. So you run through a couple of requests with edge cases, with common cases, and you see whether these requests are having a sensible flow in the system at a high level. The other thing that you can do is you can use sophisticated tools to load test this design. You can have some sort of capacity estimation to actually see whether this design is feasible. But importantly, you have to test this design before you start getting into the code. Okay, let's recap with an example. Let's say we have a live streaming system. How would we go about designing this? Requirements would be streaming video, processing video, sending video to multiple customers, so that is broadcasting. Not failing is a requirement. Showing advertisements, allowing reactions, showing disclaimers or news flashes, having graceful degradation of video quality in case you have low bandwidth, allowing multiple device support, and so on. Amongst these, you'll see that the product requirements are mainly showing video to a lot of users. That's a major requirement. And also, of course, comments is a thing and being able to react is a thing. You may also consider product requirements to be showing a banner in case there's a problem. It is. But the core requirement, of course, is just showing a video. So I'll pick this feature first. This means that I have to capture video from a source, let's say, which is shooting at 8K. And I should be able to store it in some place in my server so that I can query it later. In a live streaming system, the later part, the query it later, is probably milliseconds. So I may not want to query that data at all. I may want to directly stream it from the video camera onto millions of people. Taking a step back, it looks impractical because if I'm shooting at 8K at very high quality, and this is raw footage, sending that much data to people on their mobile phones is unreasonable. So yes, I'll need to store it in some sort of a database or a file system, and then I should be able to stream that or query that out so that I can distribute it to all of my customers. But I don't want my customers to know exactly how I'm doing this, or I don't want them to know about there's a change in implementation tomorrow. I want this to be a black box so that they can pay me and relax. They just hit an API and their problem is solved. Of course, I might give them clients which are downloadable on the App Store, which take care of all of this API and querying also, so that as end users, they can just enjoy watching an event instead of thinking about how the technical part of this is actually happening. These APIs have well-defined signatures. You can tell that if I want this video ID in a particular format, then I have to query a particular API called getVideo, which is going to be returning me objects of type frames, and those frames are also well-defined. So if you have ever written a program, you know that these API signatures are very similar to method signatures. The only difference being that these APIs might be queried not through a programming language, but through a network protocol like gRPC, HTTP, FTP, any kind of protocol which defines exactly how an electronic message is going to be taken from one place and sent to another. And also how the response is going to come back and how the behavior of this interaction is going to be. That is defined by the protocol. So this is great. We have a system which is storing some data, which is valuable to us because we want to watch this event live. And this data is going to be queried using APIs. Also, these APIs are going to be tested beforehand so that the clients who are using this, who are paying for this service, are not disappointed when they actually query it. As engineers, we have to think of various failure scenarios. What if the database which is storing your videos crashes? What if a particular firewall on the internet starts blocking all of your requests? What if one of the services that you have written in your entire system, one program, one piece of code, starts misbehaving because you have introduced a bug in it, or there is somebody who has maliciously entered the system and changed the code in that system? We'll have to use some design principles that we talked about earlier. This challenge may also be a feature request. Like if you want the musician who's playing in this live event to be able to talk to their audience, do a back and forth with some audience members who they select either randomly or based on their activity. So you have to display those users to this musician live and be able to broadcast to parties to millions of people out there. So taking these requirements, let's try to design a live streaming application. So there's two ways to approach this. One is from customers or our clients to our server, which is out there in different parts of the world, and then to our database, which may be, again, in different parts of the world. That's one way to think. And the other way to think is from our database to our server. So what kind of data do I need to store to enable my server? And what kind of APIs do I need to expose to enable my customers to be able to use my product? Okay. Both of these approaches are fine. They require different ways of thinking though. When it comes to a data-based approach, you will need to consider what kind of data do you need to store. And often you'll be thinking of these pieces of data as tables. So you need to store a video with an ID. The video has a name, it has a size, and it has some data. That's one way to think. I prefer the other approach where customers define their problems, which are then fulfilled using APIs on the server, which are then fulfilled by storing some sort of data in the server, in the database. And that data is then mapped onto tables, like so. And so for this system, this is the approach that we'll be using. Okay, in our case, customers are live streaming customers. So they may be streaming from their cell phones or laptops or the TV. And we can't assume which device is being used more often. In certain countries, you'll have certain devices being used more. There could also be a tablet, of course, from which they're streaming this video. But you see that there are multiple devices which need to be catered to. This is a front-end UI design problem. System design is more to do with the distributed systems back-end part of things. There is some system design involved when it comes to API interactions and how to store or cache data on the front end. But that is not what we are focusing on here. We are focusing on the back-end part of this system. Okay, so these clients need to be able to query our server in real time. So what does our server need to have? Its APIs are going to be something like get video, and you pass in the video ID, and you pass in your device type. So I send you the resolution based on your device type, and you might have a particular offset that, I've already seen the first 10 minutes of the video, show me everything after the 10th minute. If I have a video API like this, I also need to return something. So the return type could be some frames, some video frames. Let's say each of these frames is 10 seconds long. So a single frame is what I send back, such that it is of this video for this device and after 10 minutes. So 10 minutes to 10 minutes and 10 seconds, that frame is picked up and sent to the client. If you know about API design, you see that this API is not well named. Get video means you get an entire video, but you're returning a frame. So maybe we can rename this to get video frame. Another thing is if you're using a REST protocol, get is going to be defined in the request itself. So GET over here is going to say that get me video is enough to say that you want a video. In our case, like we said, it's a frame. So maybe get frame or get video frame is what we are looking at. You'll notice that Vimeo also has a similar API when it comes to getting the next 10 seconds. YouTube also has an API which tells you from which point to which point do you want to see the video. So I'll give you all those frames. Great, so we have this. What else? You should be able to comment on a video, okay? So what you should be able to do is you should be able to post a comment. Again, I'm using a well-known concept in REST. Post means you want to put something in the server. You want to manipulate some data, you want to add some data to the server. So if I say post a comment with an ID, here I don't care about which device it is coming from because the comment is just data which has to be persisted in the server. Based on that, I'm not going to be changing my response or changing the behavior in which I'm posting the comment. So I don't need that. I don't need an offset, but I do need the comment data. I need the author of the comment. I need the post on which this comment was made. So maybe the video on which this comment was made. So the video ID. And similarly, for each requirement, we can expose APIs, which will allow us to query and manipulate the data as we want. So that roughly defines our server-side capabilities. Okay, we haven't spoken about anything in detail. We haven't talked about the network protocol also that we are going to use, but roughly this is what it is. Okay. Now let's go for the next part, which is the database side of things. What kind of data do we need to store to satisfy these APIs? Returning frames is something we want to do. Storing comments is something we want to do, and also probably get those comments. So, and to get video frames, we also probably need to put video frames. What kind of database should we use? Comments are rather simple. You can store this in an SQL database such that an SQL table having an ID over here, the data of the comment, so text being stored as a column, the author, which is a foreign key to a user table, right? So in a user table, you have an ID, and this author is going to be mapped to an ID over here. Along with that, we have a video ID. So there's a video table also, which has an ID and some data. The video IDs are going to be mapped in this way. Okay, an example of this would be video ID 10 is over here. This is a cricket match. Video ID 11 would be a musical event. Okay, and this is a comment table. So for this cricket match, a comment was made in which they said, hey, and the author was author number 1. Author number 1 happens to be Gaurav. That's their username. So if you have to display all comments in the front end for a particular video, what you want to do is you want to get all of the comments in this table for that video 10. Then you want to get the data for that user because you want to display the username who has made that comment. And you also want to get some video data because you have to display that on top of the page where the comment was made. So in this way, we are able to satisfy our requirement of posting comments, posting video. Now, overall, this system is complete. We have a system which can answer queries. Okay, this is good enough to start with. This diagram is not incomplete. It's very, very rough or high level. There's nothing here which is concrete. Nothing which is, let's say, useful when it comes to implementation. At this point in time, we have a rough idea of how we are going to be talking to each other, not what we are going to use to make this happen. So let's get into those implementation details. Firstly, on the client side, is there something we need to do? Yes. Different APIs require different behaviors. Posting a comment means that I'm posting this once and I'll be querying that comment maybe soon, but it's not like I need something to keep happening. I don't need continuous updates on the comment. Those notifications can be given periodically to me. Or maybe I don't need those notifications at all. After a few months, I just don't need notifications on that comment. So you see over here, you have non-real-time behavior. What about a video frame? When I ask for a video frame, I usually need to ask for the next video frame immediately after that. So I'm watching a live video. I ask for a video frame. I'm sorted for the next 10 seconds. In 5 seconds, I'll be asking the next video frame. So that behavior is different. It's a more continuous behavior. Okay, so maybe we need to use different network protocols to make this happen. What would I use for a comment? I would use the most common network protocol when it comes to distributed systems, which is HTTP. HTTP gives us the benefit that you have a stateless server. You don't need to store any information when you're handling a request. A stateless server is basically, I have no idea where you're from or what you want. Define everything in the request. Okay. Gaurav Sen wants the next 10 seconds of video. What do you mean by the next 10 seconds? Who is Gaurav Sen? Okay. So what should be there in the request is, here's Gaurav Sen. This is his user ID. You can actually go and look it up in your database. It's not the next 10 seconds that he wants. He wants the video from minute number 10 to 10 minutes, 10 seconds. Okay. That video length is also well defined. There is no concept of the next pointer here. And the video ID is mentioned. It's not like Gaurav wants the next 10 seconds of the video he was watching. No, I have no idea what video he was watching. You define which video needs to be pulled up here. You might think that this is an obvious point. Like, what's so special about defining everything in the client itself. It looks a little tedious and stupid, but doing it is fine. Doesn't everyone do it? Not necessarily. When you ask for the next 10 seconds of video, for example, very often as a client, you don't know what the next 10 seconds should be. Take an example. Give me the video at 10 minutes. Then 10 seconds from 10 minutes. Okay, that's one chunk. Let's say you make that request and the server is taking time to give a response. Now you come back and you say, give me the same video because you didn't receive it in time. The server is going to look at that request and serve you the same response again. The other approach to this would be the client making a request, give me the next 10 seconds, where next is known to the server. Okay, so here the definition is not 10 minutes to 10 minutes and 10 seconds. The definition here is the next 10 seconds. The server is now going to take this request, look at the user's current pointer, and then decide which 10 seconds to pull out. So in the first case, it will take 10 minutes to 10 minutes, 10 seconds. In the second case, it's going to make a decision to send you the video from 10 minutes, 10 seconds to 10 minutes, 20 seconds. What's the benefit? The client didn't need to know which part of the video it wants to watch. It lets the server handle it. It makes the overall network more efficient because the client is not making duplicate requests. And it makes the client code a little more simple. You don't need to define everything every single time. You let the server figure it out with context. That's the difference between a stateful and a stateless protocol. HTTP is stateless. Its benefit is that the server is kept simple. If the server crashes, there is no context or memory that is lost in the server. I mean, if you forget where the client currently was pointing to, then this is a serious problem, right? You can go and store it in your database instead and make a server stateless. Therefore, the protocol that you're going to use, HTTP, can be stateless. The best part about this is you can add new servers without any issue. You have no state being stored in server. So whenever a new server pops up, a new request comes with total context in the request itself, which you use to query your data. Right. What about video frames? You want to query video frames. You want to get the next one. What kind of a protocol will be nice? You can use HTTP here also, but a much better protocol would be something which is designed for video transmission. Because in video, you have to consider some other parts. What happens if I have a mobile device which does not have much resolution? What happens if I have poor bandwidth? What kind of video am I transferring? If it's a live streaming thing, then the current video is the most important video. What happened previously does not matter anymore. If I miss that packet, if that packet was dropped in the network, let it go. If it's a live streaming lecture where there needs to be full context to understand the next part of this lecture, then you probably want to send it properly. You want to send it over a reliable network and over a reliable protocol. Okay, so if you want a reliable protocol, a TCP-backed protocol is a good idea. If you want a real-time, efficient protocol, then a UDP-backed protocol is a good idea. So over here, I'm going to use a protocol like WebRTC. Here, WebRTC is a peer-to-peer protocol, so you actually are able to send video from the server to the client. Certain protocols have a client-to-server expectation. So the client is the only person who can send data, who can make a request to the server. The server cannot send data by itself to the client. Okay, so what I'm doing again here is using a peer-to-peer protocol for the video, but for comments, it's always going to be client-to-server. So you see that network protocols are also important when it comes to designing systems. Okay, finally, on the server side, what are some considerations we have to take? Similar to the server side, we have to think about how are we going to talk to the server. But most database solutions, let's say MySQL or Postgres, define exactly how you're going to be talking to the databases. So this is a TCP-backed protocol usually, but the protocol is defined well. So we don't need to think of that when it comes to talking to servers. Elasticsearch, for example, has a HTTP-based protocol. Cassandra, Amazon DB, Amazon DynamoDB, MySQL, Postgres, all of them, the protocols are well defined. The problem then becomes which database solution should we use? Because there's a ton of solutions out there and they have trade-offs. We could store data in the MySQL database also, but it's going to be expensive and it could be potentially very slow also. So what is this video data? It's effectively a file. So storing it in a file system is not a bad idea, right? And you don't want to build a file system yourself. So you want to use a well-known file system solution for this, maybe HDFS. That's one solution. You could also use a video hosting solution like Vimeo. Yeah, it's off the shelf. You can just use it. You can use Vimeo, by the way, to host events also. So it's best to mention this in the system design requirement. Like maybe an enterprise solution from Vimeo will take care of the entire thing. But if you can't do that, if you can't have a live streaming requirement and you don't want to lose your job, maybe because that'll go over to Vimeo then, you can use a file system like HDFS or S3, Amazon S3. The benefit of S3 or HDFS is that it is cheap, it's easy to query, and you can store very large files inside it. Okay, in a database, yes, it's not cheap, but it is easy to query, and you can store very large files inside. The capabilities that a database gives you in terms of updating data or querying data may or may not be very relevant to you when you have a static file, which is a video file. Okay, you're primarily looking at low cost when it comes to storing video solutions. What about the user or the comment table? These two tables can have SQL solutions back in them. Let's say MySQL or Postgres. You may say that a comment is a complex data structure. Every time a requirement changes, the comment table also needs to change. Maybe you want to persist a lot of data in the comment table per entry. You want to persist all the replies of the comment also in the same entry. So a MySQL database or a SQL database is not what you're looking for. You're looking for a NoSQL database, which is not ideal when it comes to transactions or relational joins. But you don't have that requirement. You're looking for scale when it comes to comments. You just want to persist that data in a key value fashion. So that's NoSQL. Great. This is a very rough idea of how we are going to be designing, which is satisfying the requirements of the system, and also defining the protocols or the solutions that we'll be using to make it possible. For example, we talked about WebRTC, HTTP when it comes to network protocols. And when it comes to database solutions, we talked about MySQL and a file system. A design can go in more and more depth based on how important that requirement is. So doing a recap, we see that we have a system, a very rough blueprint even now, which talks about how our customers are going to be accessing our APIs and how those APIs are going to be accessing the data in our database. The data in our database may be being filled by customers, like in Facebook, usually the customers are the people who are filling the data, or it may be filled by an external service. In a live streaming system, it's probably going to be a really high definition camera, which is going to be recording the video live and persisting to a database. Okay, the network protocol that you probably want to look at is RTMP, real-time media protocol, which is a guaranteed protocol. You don't lose any data when you're shooting video using this. And the idea is WebRTC, you might lose some data. That's okay. It's the end user watching a live stream. They want data quick and real. But at the source of everything, you don't want to lose any data because everybody else will lose the data if you lose it at the source. So a highly reliable network can be set up over here. High bandwidth, expensive network, because that video camera is really going to need a high bandwidth, expensive network to persist that amount of data into your database. And then this data can be sent. You're seeing that I've skipped a lot of requirements. You see that I can't take this high quality data and just send it, broadcast it to everybody on the planet. What I'll need to do is transform this data. Okay. So now what we are doing is we have looked at a high level what the solutions are going to be. And now really getting into the nitty-gritties of designing the system. So the first part of this is, how do we take this raw footage, this data, over the highly reliable network, which comes to our database, our file system, and convert it into data that we have to serve our customers, 480p, 720p, so on and so forth. You can't serve 8K definition. So how do you do that? There needs to be some sort of a transformation service. over here, which is going to be taking this live stream and converting it into different resolutions. So 1080p, which is full HD. You have 720p, which is HD, 480p, which is decent for quite a few mobiles. And I don't know if this is something you want to do, but if the live part of your stream is really important, then 144p is also okay. Because as long as people are getting information and they're able to see roughly what's going on, they're going to be happy. Sometimes these resolutions are defined well in the product requirement document itself, the PRD, because after speaking to customers and getting their real feedback, you know which resolutions are acceptable or tolerable for the customer. There might be some customers who ask for premium 4K transfer also. Okay, so that's fine. I mean, you're watching it on TV, then you probably want to watch it at 4K. Okay, this raw video needs to be converted to these resolutions. How do you do that? So the first thing you'll do is you'll break this video into segments. This entire raw video is going to be broken into segments of 10 seconds. So you collect video for 10 seconds, you chop it off, you break that into one segment, and then you give it for processing at point number 0, 1, 2, 3, and 4. So let's say you have these 0 to 4, which is 5 programs, which take the raw video and convert it to different resolutions. So if you pass in 144p, then a particular program picks it up. If you pass in 480p, then another program picks it up. And maybe you have the same program which is running in 5 concurrent pieces, in 5 threads. Based on the resolution that you pass, it converts the video, the 10-second video footage, into that resolution. Similarly, you can think of different formats. So if you have a device which is an Android device, it probably has to see the video in a different format. Okay, it can't read all sorts of video. It has some formats which are well defined inside it in the device, so it can read that format. Similarly, Apple devices might have a different format. So these formats define how you're going to read this piece of data, this video data, which is going to be sent over you through the network. Common video format is H.264. Apart from H.264, you might have your own proprietary formats. Let's say you have a format which is more efficient than H.264, or for your particular type of event, a music event, you research and you find that there's a way to store video more efficiently. So this is more of a very large scale problem. Like Netflix has its own formats, but if you're a small company, yeah, H.264 is very good. Okay, so different resolutions, different formats. We need to take our raw video footage and convert this into a combination of a resolution and format. So over here, we use a design pattern of map reduce. I won't go into too much detail of this design pattern, but the basic idea is you can take one video, split it into pieces, which is 10 seconds long, and send it to different servers to get different outputs. Okay, you might have something else also in the process. Apart from just transforming the type of video, maybe you want to compress it here in the next step. That can be in step 2. The servers being used here might be S3, S2, and S1. So you see S1 is being used here and here. S3 is being used here and here. So there is no guaranteed execution server that you have for one part of the process. Any server which is free will pick up a task and execute it, whether it's compression or transformation. Again, finally, you get 3 different outputs, which you can store in your database. So this would be the map reduce pattern. It's a very high level overview of this. It's almost a caricature of the map reduce pattern because there's no reduce in this process over here. But have a look at this design pattern. It is useful when it comes to taking a single piece of data or a data lake and converting it into the data streams that you need. Next, how is this data actually going to go to the users who are looking to view it? So this data has to go over here to the server, right? Which is exposing these APIs of get, put, post. When you query this data using a protocol, you should be able to get it. We spoke about WebRTC earlier, which is a peer-to-peer protocol, and it's really good for video conferences because multiple people are streaming video together. However, in this case, it's a broadcast, not a conference. So we can take a step back and say, instead of WebRTC, we are going to use a protocol which is more suitable for streaming. There's a couple of protocols here also. The most popular one would be MPEG dash. MPEG is a popular protocol. Dash here stands for Dynamic Adaptive Streaming over HTTP, which means that depending on your bandwidth, depending on the network that you're on, you're going to be able to see high quality video or low quality video. For example, you're going in a car, you're watching the video at 1080p, you enter a tunnel, your network is really, really poor, so you start watching it at 144p. As a client, you don't want to handle it, you want the network protocol to handle it. It's defined in MPEG dash. Another very similar protocol is HLS. This is useful for iOS or Mac devices. Okay, and finally, what kind of data do you want to store on the server? Do you want to store any data at all? Do you want to make it totally stateless? Yes, statelessness is useful when it comes to request serving and keeping context for every user. But for some things, you can keep some state. Like when it comes to video, you can cache the last 10 minutes of video on your server. So anybody asking for video in the last, that video which is inside the last 10 minutes is going to get it from the cache instead of you making a full network call to the database all the way over here. You instead serve it from server itself. So you avoid this network call, saving time and bandwidth both. So these are the high-level considerations that you have when it comes to a system design. Like we said, this is a large-scale distributed system. Our assumption is that you have a lot of users, because of which this much planning and this kind of a design makes sense cost-wise and engineering effort-wise. We mentioned that there needs to be fault tolerance here, there needs to be performance here. So you can use things like CDN solutions. So you can use content delivery networks to persist some static data and have the clients actually pull the static data from here. Web pages are a good idea. You can also have some video data posted on the CDNs. In which case, authentication becomes a bit of a challenge because you don't want everyone to be able to see this data. And does the CDN do the authentication for you? Do you write some code and then host it on the CDN, which does the authentication? These are the challenges that you have, especially when you're designing a large-scale distributed system where performance is key. Okay, so this is at a high level, the things we need to consider when we are designing any sort of a system where the requirements are defined, maybe in a product requirement document, maybe it's a startup, so it's at a very nascent stage. There is no requirement document. You're directly talking to the customers and coming up with a technological solution which is going to satisfy the requirements. The important things to notice are that you define the requirements as abstract concepts, like objects. These objects then need to be able to be manipulated and queried using APIs on your server. The data representations need to be stored in databases. Once this high-level blueprint is done, we start thinking about what exactly do we need to make this system possible. So what protocols are we going to use? What kind of database solutions can we use? In some cases, you also think of what kind of intermediate design pattern solutions you can use. Like you have load balancers, you have message queues. These are all design patterns, and these have been converted into tools by various companies. Redis, for example, provides caches. Load balancers and many other things are also provided by cloud solution providers, AWS. You want to use these already well-built, well-tested solutions instead of rebuilding it yourself, unless the trade-off in terms of cost and performance is significant and it's worth it. Finally, once you have decided on the tools, you think about the interactions of these tools and the interactions of these services to meet your requirements. So we thought about how are we going to take a video and show it to the user. Oh, well, we have to transform that video. We have to convert it into different formats. Otherwise, it won't be visible in different operating systems. We then thought about how we are going to stream this video to the server. We then thought about how we are going to stream this video to the client device. And finally, we kind of touched upon actually streaming the video through a CDN solution instead of from your server. Because maybe your server is in the US, and even if it is close to the person who's streaming, you don't want your server to handle all that load for some static content. You want to be giving that load away to well-known solutions like content delivery networks, which can be tied up with their ISPs. You can have a look at how Netflix does it here. Another part of system design is low-level design. This is in contrast with what we just saw, which is high-level design, where we took different components of the entire system and thought about how those components are going to interact with each other using network calls, using APIs, and then you're going to be sending data from one place to another. But largely, if you look at these systems, they own the business data related to that service. Now, what we are going to do is take certain functions of these services and try to code it out, which means we are going to go into much more depth. But because of that, we are probably going to lose some breadth. Okay, when you look at the high-level design of a system, you're looking at everything from how the users will be interacting with your gateway. The gateway is going to be actually sending these requests to your internal services. The internal services are looking at databases. You can't code all of this out. Even in at work, you can't just have this all in one document, one page. So you take small chunks of the system and you try to elaborate on each chunk. That would be the low-level design. The core functionality of live streaming is to be able to view a video as a customer, as a person who's paid. Maybe it's a subscription, maybe it's a one-time purchase, but what we are looking at here is how does a user fetch video, view video, and fetch more of the video and continue doing so till the video ends, right? We are not looking at onboarding the video, onboarding a movie, or how the live stream is going to be moved from the source camera to our system. We are looking on the other side, the user side, of how it's going to be consumed by the users. To do this, we again have two approaches. One is to think of the code in the start. So if you are an object-oriented programming language person, you might think of what kind of objects do I need to have in my system? How are these objects going to interact with each other? Is there any kind of inheritance I have to take into consideration? But as earlier, this is a little difficult to think of unless the requirements are extremely well specified or they are so generic that you have to look at the data that you're storing first before you think of the functionalities. I would suggest you think of the user. So even over here, we think about what are the actions that a user can perform. So what I'll be doing is on my phone or on my desktop, I'll be scrolling to a particular place to watch the video. Okay, so I'll be scrubbing the video up to a particular point. That can happen. I can also click on play from the start. So start the video at the beginning at timestamp 0. Both of these are very close to each other. So effectively, the action is play video at timestamp X. Another functionality that I need is to pause the video. Okay, in which case, what do? Do you continue fetching more segments from the backend, or do you stop fetching segments? So the behavior is dependent on the user experience that you want to give. If you don't want to clog up their mobile with the entire video while they have just kept it in the background, then you have to be smart about it. Probably the next 20 or 30 seconds or 1 or 2 minutes can be buffered into your device. So that behavior also has to be coded inside. Despite pausing, we go for the next 2 minutes of video from the place that you have seeked right now. Another important requirement is that depending on your device, the video quality which is going to be fetched is going to be either HD, let's say you're viewing it on a desktop, or 480p, let's say for low resolution devices. And one final feature is up to what point have you played a video, which means if you had a 1 hour long video, let's say there's a cricket match between India and Pakistan, and it's 1 hour long, and you have seen up to the 20th minute. If you log out and come back and want to watch the same video, we should start at the 20th minute. We should store that somewhere so that you have a good user experience. You might want to cache the video like we were doing earlier. The next 2 minutes, you want to keep that buffered so that you start playing immediately when the user has come. Or you may not want to do that. You might want to do that just for some videos which have been recently watched. The older videos then can be kicked out of the cache. You see that what I'm considering here are memory optimizations, user behavior, and API calling. This is largely what low-level design will mean when it comes to interacting with services. Depending on your level of seniority and depending on the use case, you might have issues of concurrency, latency, and throughput also come in here. An example use case will be the workflow that we had for chunking and transforming videos. I'll leave that as an exercise to you. But there are cases where you want to increase your throughput to the maximum. So you don't really care that much about latency. How quickly do you get those videos through the pipeline? That's not your concern. You want to make sure that your pipeline is continuously functioning, right? Another case is where the moment a video comes in, the new video, you want to respond to it as quickly as possible with the assumption that that video is really important. So there's going to be some sort of context switching over there. Okay, I'll leave that as an exercise to you. I won't give you too many details, but it's interesting to think about how these different low-level design requirements affect the code that we write. Similar to what we did earlier, we are going to take a structured approach to solving this problem. The first tool that we like to use is called the use case diagram. As the name suggests, we think about what are the use cases that we need to fulfill for every user. For example, you can see 3 actors in this system. An actor is a person who can do actions. So an admin can do actions in our system. They can add videos, maybe. A videographer is a person who can upload videos. So it may not be necessary that every video which has been uploaded will be added to the system. Before it gets added, it has to have some metadata added to it. What's the description? What are the timestamps? What kind of video is this? How do you tag it? So that might be taken care of by an admin. The videographer shoots the video, uploads it, specifies the quality and everything else. So that's a separate actor. And the customer, the person who consumes the video. We said that this is the most important person for us. So this is the only actor that we are going to be thinking about. Let's get rid of these 2 actors. We mentioned that there are 4 things that we want the customer to be able to do. Let's note them down. The first thing is to be able to play a video from a timestamp. Okay. Then comes another requirement, which is this is them coming back to the old video that they watched partially, and they want to start watching again from the left of timestamp. We also want to view at the maximum quality allowed by network and device. So if you're on a low quality network, that's okay. Low quality video is also fine. But if I'm on my home Wi-Fi, I want to see the best quality video that I possibly can. I've paid for this subscription. There's things which are also happening in the background. Of course, like we said, concurrency, fault tolerance, throughput. These are things which the end user does not need to think about. You might say latency is something that affects the user. It kind of does, but we are not looking into it. We are assuming that all of our requests have to be answered within 10 seconds, quickly enough. And this brings us to our next point. We need to continuously buffer our video, right? So have non-stop play when watching videos. This is assuming, of course, that bandwidth is not messed up. If your bandwidth is messed up, you can't buffer. So that's not a problem. But if my bandwidth is fine, then for the next 2 minutes, I should be able to watch the video. Okay, and this is the customer. If we can fulfill these requirements, they're going to be a happy customer, which matters a lot as an engineer. Okay, these would be called use cases. Right? You can have many use cases. Some of them are core use cases, some of them are not. When it comes to system design, the expectation is that if there is a PRD that has been given to you, a product requirement document, usually it's just on one use case, right? You add a feature and each feature is important. So we'll take all of these and mark them as reasonably important. The next step is to convert these requirements into classes and objects. This is where things usually go wrong. When you look at the use case diagram, right, it looks like everything is to do with the customer. View at maximum quality allowed by network and device. But is the customer actually doing that? Is the customer saying that, please give me the best quality video? No, that is obvious. That part is obvious. So who's going to handle that? If the customer is not going to handle that part of the system, then the system has to handle that part. Okay, so there needs to be another actor in this system, but it's not somebody who does actions like physically. They're going to be interacting with your system. So view at maximum quality offered by the network. Who's going to handle that? There needs to be some sort of a controller or the brains behind how much video should you send. So I'll just call this the rate limiter. Okay. Sometimes the entire service, the entire functionality can be handled just by using a tool. So we offload the problem to a tool. Or in our case, what would be ideal is to use a network protocol which takes care of this. Depending on my device and depending on my network requirements, you take care of the bandwidth. An adaptive bitrate protocol is going to handle this. HTTP dash will handle it. So we'll assume that this entire service, which was going to look at the user's requirements and then offer them video at particular bandwidths, can be taken care of by a simple protocol. So this rate limiter does not need to exist. Instead, whenever you're connecting to our system, it's going to happen over HTTP dash. Right, that is a pretty big deal. One entire use case taken care of just because you know what tool to use. Now, in an interview scenario, you might be asked, how does HTTP dash work exactly? How does it work internally? For that, you can either read some papers which help you learn the protocol internals. Database internals are also very similar. Operating system internals are also very similar. Or you can guess. In which case, you should probably specify that, hey, I'm just guessing over here. But I think what's going to happen in this adaptive bitrate would resemble exponential backoff in TCP. Now for the next bit. Play a video from a timestamp. This means that every video needs to actually store a corresponding timestamp for a particular user. Okay, that can be done. We need to have an object here. Our service, which is video server, a video consuming service, is going to be used by end users. Play a video from a timestamp. Okay, so this has to be taken care of by the video consuming service. So that will be play video for a user, and this is the video ID. Okay, so I'll just remove the play, put this, and I'll also mention the timestamp that is being passed here. You see that I'm still thinking in terms of APIs. The clearer your APIs are, the easier your low-level design will be. The more you think about how the users or each feature is going to be implemented using the services that you have, the easier your design will be. Okay. Go back to a video and watch from left of timestamp. This is quite straightforward. You have seek for this user and this video. What is the seek position? So let's say we call it get seek position, but like we said, if you're using a REST API, then you can mention in the method it's get. So that will send you back the seek position. It's best to mention the return type also, like I said. The clearer you make your API, the better it usually is. So video frame will be sent back here. And similarly, what will be sent back here is a timestamp. So what's going to happen is when you come back to a video which you have left off, you're going to first seek what is the position where you should go to. So that will give you a timestamp. And then you say, okay, play this video for this user from this timestamp. All right. Have non-stop play when watching videos. This is interesting. We need to get frames in future. So what do? Do we say play here or do we say get video frame for a particular user and a video with a given timestamp? Do you see that these two are very similar? Since what this API is also going to return you is a video frame. And you're going to stack these video frames together and buffer them into the video, into the phone. Yes, I see a very, very close linking between this API and this API. At this point, you ask yourself, what does the product need? Is play a different action from fetching the future content? And here I'll make a decision of yes, it is different. It's strange to think of because they are doing the exact same thing. What they're doing is that the user is saying, play me this video from this timestamp. That's okay. And the other one is that the video player is saying, get me the video frame for this timestamp. Looks extremely similar, but the business use cases are very, very different. If the user says, get me a video from this timestamp, it means that they have probably seeked that position, they liked what they saw over there, or they found it exciting and they clicked on it. So it's very different behavior compared to, hey, get me the next 2 minutes of video in the background. Okay, that's one very important thing when you're designing any API. Think about who is using it, what is it being used for, right? And then think about the common functionalities. So these two APIs are very similar. And on the server side, what you would ideally like to do is just merge these two APIs. The client should figure out by itself that what video frame does it want to pick. So maybe you cut down on the APIs that you have to maintain by replacing the current API of play with what we have here. So maybe every time you play from a particular point, we should send an event to the backend service saying that this is an exciting part of the video. The user actually came to this timestamp, seeked here, and clicked on the video. Okay, you see that there is a seek API, which is primarily for when you have left off a video. So if you left off, came back, and started watching from there, maybe it's not super exciting. It's just the place that you're leaving off from. You want to continue from. But during the video, while watching it, if you came to a particular position and started viewing, that requires an event. That shows that this part of the video is sought after. So it feels like you're splitting hair here, but from the side of the business or from the side of analytics, they are very different use cases. From the side of engineering, it's the exact same behavior. Someone asks you for 10 seconds of video, you give them 10 seconds of video. But for analytics or for the business, this part should be converted into a trailer. This part is just for user experience. So it depends on you as an engineer. I personally would take this API and I would see who's making this request. So a flag would probably say that the user made this request or the device, the mobile, made the request for good buffering. And depending on that flag, I would then fire an event for showing interest in this part of the video. All right, so that is the use case diagram. We can now think about the class diagram. Let's draw the class diagram out. The first class that we need is a video. Two things that we need to store for every class are states and behaviors. States are data that an object needs to perform behaviors. For example, I'm speaking right now, so I need a throat, I need a tongue, I probably need a brain to speak. And what I'm doing right now is teaching. So the behavior would be teaching, while the data that I need is my body parts to actually work in tandem. Similarly, you might have a video which has certain data that it needs. So that would be the bytes of the video, or let's say frames, because we have been using this term. That's in every video. You might have some metadata like who's the uploader of this video, how long is it, what kind of tag do you want to add, so on and so forth. What operations can you perform on the video? Well, you can get a frame, right? That's pretty much it. Okay, you can't add a frame after you've added a video. You can't do anything apart from just getting a frame from a particular point. So that's a simple class. You also have the class of user. You see that I'm now focusing on the class diagram. So user has a name, an email, more metadata around them, but nothing else really. The most important thing probably will be an ID. In your case, could be an email. Video also will have an ID. And for a user, you can probably get their ID. Okay. Very simple class again, which brings us to the most exciting class, which is watched video. Okay, so a watched video is going to be an action by a user who's basically watching a video. So This needs a video ID. Which video have you watched? Who is watching it? That is the user ID. An ID of the action so that you can refer to it later. Up to what timestamp have they watched this video? So seek timestamp. And coming back to the use cases, we might want to buffer up to a particular point, but let's assume that the client handles that. The client knows how much video you have buffered already in the device. Going back to a particular place is possible because of the timestamp. The final class is video consuming service. This also requires a class to be explicitly shown here. So that is video consuming service. Let's first define the behaviors that this class has. So that is API 1 and API 2. And to do this, it just needs a set of watched videos. Which will tell it which user has seen what video. Okay, that takes care of our entire class. You see, this is a very simple class diagram. What is more challenging actually is the sequence diagram. Okay, how is a user going to watch a video? So this would be called a class diagram where we have defined what state and what behaviors are possible for each object in our system. Fine. These two diagrams of a class and use case are sufficient in most cases. However, in some places where the interaction is complex, like over here, you need another diagram which defines the sequence of actions. In this case, it's not very clear how the user is behaving. These are the actions that they can do. Okay. These are the things that you need to store and the behaviors you need to expose for the action to happen. That's also right. What is the sequence of actions? What happens first? What happens second? That's not clear. And for that, you need a sequence diagram. So let us try doing that. This is what you call a timeline. The y-axis basically is time, but in descending order. So you have three timelines here. One is that of a user. A user does certain actions. Things happen to a video. Okay, and the video consuming service actually uses a video's current seek time to get the next frame. So this might not just be a video, it could be a video service which is providing an API to consume the next frame of the video. We'll see how this happens. First, the user sends a message. What message is this? Right? Like we said earlier, this is going to contain user information and the video information. This is responded to by the video consuming service immediately because it knows up to what point has a user seeked a video. So that is, you return a timestamp. Now the user is going to make another interaction, which is play or get video frame, right? So get me the video frame as this user or this video at a timestamp. And the tool I'm using here is Lucid Chart. As you can see, if you use tools, it helps. Instead of reinventing the wheel or doing it in a haphazard way, this is much better. The video consuming service cannot get you the frame though. However, it's best that the user interacts with the video consuming service. So it could send a message to the video service and say, get me the video frame from a particular timestamp. Okay, the important thing to notice here is that the video service has no idea who the user is, whether they're authenticated or not to watch this video, and it just gives you a timestamp. Okay, I could have taken this request and sent it directly to the video service. Okay, and the video service could say, sure, I don't care about which user is trying to access this video. Just tell me the video and the timestamp, and I'll give you the response. But authentication would be a bit of a problem. So that's the reason why I'm assuming authentication is going to happen here for every frame that you ask. And then the video timestamp has been mentioned. I'm going to be sending back a response of a video frame. I could also send back multiple frames in the hope that you can use them later. But I'm assuming that a frame lasts for 10 seconds, and if you really feel like you can send a request in between and get another frame. So it's a single frame, and this is then sent back to the user. Okay, that's the interaction for a while. The moment you get a frame, you want to repeat this action. And so the data keeps flowing. Very similar to how a TCP connection works, actually. Initially, you have some sort of a handshake, right? You get some initial information, set up the connection, and then what's happening is you're constantly pinging. One of the drawbacks that I can see here in my diagram is that the video consuming service is an intermediary. There's so much communication happening between the video service and the user. This is just wasting time. I don't know if that is worth it. If just authentication is worth complicating our flow this much. I mean, you can put some authentication here in the video service itself. So you'll save on 2 network calls, which is a lot. So yeah, maybe I should just take this, put this here, and take this, put this over here. Right? Don't go into the video consuming service. That's what we'll be doing in the code. So now we finally jump to coding. Remember to use the diagrams that we have made as a reference because most of our thoughts and most of the interactions are documented well over there. It would be a waste not to use it. The whole purpose of making these diagrams is to take away the thinking effort required while coding. Coding is basically us typing out or writing the things which have been mentioned or thought through in these diagrams. Okay, that will speed up things and also help you avoid mistakes. So the first class that we talked about is a video class video. The state that we talked about is it has an ID, it has frames, so maybe a set of frames here, but then the frames are also ordered, so an array of frames makes sense, and then some metadata. So in our case, I'll just say metadata JSON. Of course, in the real world, you would actually have the creator of the video, the uploader of the video, and many other parameters, the length of the video, everything else. But we don't need that right now. So I'll just create a class. You see that an ID helps you create classes much better. These classes that I'm creating are just plain Java objects. You can use the same thought process for C++, for C#, and many other languages, any object-oriented programming language. If you're coding in Python or Scala, it might be slightly different, right? But the logic is very similar. Come to the point of defining things as objects and the interactions between them, and finally define the states and the behaviors of every object and then code them out. Okay, so this is largely language agnostic, this approach. You have a video which needs a frame. A frame is going to be a bunch of bytes, so that's okay. And maybe it has a timestamp. So that is int timestamp. You also have a class of user from the diagram. User has a string ID. It has a string name, string email. These are basically metadata. And we talked about some behaviors that these classes need. So return a frame when someone says get frame. And which frame should we return? We should return the frame which is being called for a particular timestamp. So you see our class diagram had missed that. Now we can go back and fix it, or we can fix it in code. I would suggest fixing it in both places, because if the documentation is up to speed, it helps. In timestamp, you can also have timestamp as an object for making sure that the integer is greater than 0 and all that, all the validations that you want. But I'm just keeping things simple. Pass in a timestamp here. We are going to be iterating over the frames. This can be improved, of course, but what you want to do is you want to go over the frames and return the timestamp and return the frame only if the timestamp of the frame is less than the timestamp you have asked for, less than equal to, and there also has to be some sort of an end timestamp. So we can assume that every frame is of 10 seconds, in which case the start time is this has to be less than equal to, and the end time mentioned over here plus 10 is greater than or equal to this timestamp, okay, or rather greater than, then this frame belongs to this. If you don't get the frame, then you just return null. You can also throw an exception here. So let's see. I would say throwing an exception makes sense, because the meaning of an exception is that I didn't know how to react to this. Null would mean that, oh, you get blank. So if a timestamp of 20 hours is sent for a video having just 1 hour, a blank frame is not exactly what you want. You want to say, oh, you're out of bounds. So index out of bounds exception being thrown here is going to be useful. Okay. Now, there's another small problem I see over here, which is the magic constant of plus 10. You don't really want to do this. It doesn't look good. Because tomorrow, if your frames get optimized and can store 30 seconds of video, then you have to go and change it in the code. So you might have this in a constant in the video itself. Let's say a class constant. So public static int frame time equal to 10. And then what you have is, if you need to make any change, then you make a change in a single place. But even that would not be suggestible, because this is something related to the frame. So let's take that, put it in the frame class, and then what you have is frame.frameTime. Has to be this. But that is also, that's fine. It's good. There's just one data point for the entire class. All of your frames have the same amount of frame time. It could be different. It could be that these frames, some frames are really high quality. There's a lot of movement over there. So it's not even 10 seconds long. It's just 2 seconds long. And some frames are, like this coding frame over here. You can store 10-15 seconds of video because there's not much happening over here. There's not any face moving or something. So I'll just take this and I'll leave it to the object, not the class, but the object. So it does not become a class property, which is going to be for every object. It is defined by each object. So end timestamp and then this becomes start timestamp. All right, so this is better. I don't need to mention start timestamp. I just say end timestamp has to be greater. Okay, this is much more flexible code. This is what will set you apart from just a coder. You're going to be an engineer then. Okay, so now we have a user. You can get their ID. So this is not really related to what we are doing, but that's okay. Int get ID and return the ID string. Okay, the next class is more interesting. There's watched video. which is a class. Here we have the ID of this action. We have the video ID. We also have the user who's actually watching this video, who's doing this action. And we have a seek timestamp. So that is seek time. Okay, we mentioned that there's going to be a method to get seek time. Important to notice that APIs having REST have the keyword get inside them. Often, like, you can mention that you're posting something or getting something, but the objects here can have a get of their own because you don't exactly know what's happening, right? It's not a HTTP API here. It's a Java object. So get seek time makes more sense here. So this defines everything except for the last couple of behaviors, which are actions by a user or actions by a system. So the video consuming service, show me the seek time. So this is going to be a public int seek time return for this watched video. So seek time had a user ID and a video ID. Let's assume that watched video is a database call. And once you have this watched video, what you want to do is you want to get the seek time and return that. Okay, so for this to work, we need to have a database. Which we are going to create as a dummy object. Okay, let's create that and return that. Okay, this is great. It gives you the seek time. And then finally, the other API that we looked for is class video service. So the final class is going to be using a file system, let's say, because videos are usually stored in a file system. And let's define that class, this class file system. Okay, now there's a public method similar to the previous service, which is going to be returning a frame, and that is get frame for a particular video with a video ID and a timestamp. Okay, and how's the interaction going to happen? We first need the video. So let's say our file system gets us the video with this video ID. Once you have the video, you need to return the frame corresponding to this timestamp. And that's it. That's pretty much it. You have something backing your services, some sort of database or file system. Once you have them persistent, you can always get to them and pull data from them. Once these systems are being backed by a database, then you can actually manipulate this data that you have by exposing APIs. And the best way to manipulate the data is to abstract them out into objects which have their own state and behavior. So the code is simplified and you can reuse a lot of the behaviors for different types of use cases. This would summarize the low-level design process. All right then, that's a reasonably well-detailed introduction to system design. If you want to look at more videos on system design, there's a free section that I have on Interview Ready, which is all about the design patterns and the basics of system design, load balancing, rate limiting, sharding, and scaling. And if you want a more advanced version of system design, I have a paid section in that same course. I would suggest go ahead and check out the free resources first. If you really like it and you think that, it's time to level up, go for the paid section. All the best.